Uh, Good afternoon, everyone. Can you guys confirm if you guys are hearing me clearly?
Yep.
Okay, I want to welcome everyone to my lecture today. Okay, today, um, the focus is actually going to be on time series, just like what I said. But you know what? How do we get to where we are? You know, I actually want to first present a framework. I could remember at the beginning of the semester, I started with basic statistics review. And of course, I did basic statistics review just for you to be able to have the background knowledge of approach of statistics. Okay, I think I started with that, and from there I moved to linear regression. We did a lot on that linear regression. In linear regression, I actually where I walk you guys through simple linear regression and multiple linear regression, and of course, the simple linear regression is a way to fit a model to enable us to characterize relationship between two variables, one response and the other one predictor. And you know what? The response is continuous. And of course, I walk you through some assumptions on the line, the use of the method that we use in estimating parameter, okay, in simple linear regression. And I we did a lot of stuff. The takeaway from simple linear regression is just that okay, we are actually assuming that the relationship between the two variables are actually is a straight line. From there, we move to extension of simple linear regression is actually the multiple linear regression. We are still assuming a straight line, but only that this time around, the numbers of predictors is more than one. Okay, you can say the numbers of predictors more than one, or the numbers of regressors are more than two. Okay, so with there we also talk about some assumptions underlying the use of multiple linear regression model. I in addition to the assumption that we have in the simple linear regression model, we added another assumption under the multiple linear regression model, the assumption that we call multicollinearity. Okay, situation where the predictors variable actually correlate. And you know what? Whether you are dealing with a simple linear regression or you're dealing with a multiple linear regression, of course, we have a way to evaluate whether our models are fantastic or not. Okay, and the way to validate is to revisit our assumptions of the simple linear regression and the multiple linear regression model. You remember we revisit the assumptions of linearity, the assumptions of normality, the assumptions of constant variance, and there is one assumption that we did not actually treat in this class, which I call the assumptions of independence. And somebody has a question the other time. I say, okay, you know what? If you actually collect your observation where you use the principle of randomization, of course, the assumptions of independence is already met. Okay, I remember I told you the other time that if observations are collected independently, of course, the assumptions of independence, okay, has already been guaranteed. But I want to tell you what we're going to do today is when there's a violation of the assumptions of independence, because the time series that I'm actually going to walk you through, the assumptions of independence is actually violated in time series. Okay, before I go into the time series, I know we're still on the journey. And of course, after diagnostics, whether in simple linear regression or in multiple linear regression, after diagnostics, if there's a problem, or probably if any of the assumptions is violated, of course, we can actually go for power transformation. Okay, I think you know that. We go for power transformation, and I actually walk you through how you can actually transform your model. In fact, I brought out a question like that during the midterm too. Okay. In the in multiple linear regression, we also do. I remember I walk you through what they call variable selection. Of course, I walk you through what we call the partial F test. AI forward selection with BIC. Then I also walk you through what we call the backward elimination. We did the backward elimination with the AIC, the backward elimination with the BIC, and so on like that. So I walk you through the process of variable selection. Okay, in when we're dealing with the multiple linear regression, and of course, recently, when I also walk you through what I call the logistic regression model. And of course, we're able to have the logistic regression model in a situation where the response variable is actually categorical. And you know what? When the response variable is categorical, of course, there's going to be a violation of linearity. Okay, there's going to be a violation of linearity assumption. I think you know that. And that was why we actually, I walk you through the logic transformation of the linear regression, and that actually took us to logistic regression, and we're able to have a sigmoid function that we use in capturing the relationship between the categorical response variable and predictor. Okay, I want to tell you the extension of linear regression is a logistic regression. Okay, the logistic regression is a generalization of linear regression. I think you know that, because if, all what we're still doing, whether you are using logistic regression, any regression other than linear regression, I want to tell you they are actually generalization. Okay, you guys confirm again if you guys are still hearing me clearly.
Yes.
Okay, thank you so much. Thank you for confirming that. All what I'm trying to tell you is that any other regression, whether logistic regression, whether Poisson regression, or whatever regression, that is other than linear regression, they are all generalization of linear regression. Okay, the whole process, the whole thing actually starts from linear regression. And the moment it is not linear regression, then we need to look at the nature of the response variable that will be able to know the appropriate, the type of regression that we're actually going to fit. Okay, I also walk you through the Poisson regression. Of course, I told you in the Poisson regression, when the response variable is a count. Okay, when the response variable is not continuous, or okay, and it is not categorical but a count, okay, then we're gonna make use of Poisson regression. I think we did that yesterday. But you know what? Today, I actually want to walk you through a time series analysis. Okay, let's get started. But I want to tell you this: the time series analysis. When I talk about time series, I'm actually talking about data set that are collected over time. Okay, data that they said that are collected over time. Okay, when data set are collected over time. Okay, the data set I'm talking about could be daily data, could be weekly, could be monthly. Okay, uh, because they are collected over time, there's always going to be a violation of independence assumption. I want to tell you the reason why we cannot use linear regression for time series data. Because the reason why we cannot use a linear regression for time series data is because, there's a violation of independence assumption. Because if I'm talking about daily data, maybe for instance, I'm talking about the volume of sales in my restaurant. Of course, I want to tell you the volume of sales probably on Tuesday could depend on the volume of sales for Monday. Okay, so there's always going to be a violation of independence assumption. Okay, and that is the reason why we're actually going to use a special statistical analysis that we call time series analysis. Okay, now I want to officially welcome you to time series analysis, and I need you guys to confirm if you guys are still hearing me clearly. Are you guys still hearing me clearly?
Yep.
Yep.
Okay, thank you so much for confirming that. Okay, we're good to go. So, like I said, I'm welcoming you to time series analysis. Okay, like I said, the time series analysis is actually the data that are collected over time. Oh my God, take a look at this Mississippi National River. I'm missing this river a lot. Okay, but I know when we return to in person, I'm actually going to visit this again. Okay, now take a look at what I'm displaying right now. The Mississippi National River, okay, is actually attracts a good number of visitors yearly. Okay, now what you can see right now, we have a data set from 2011 to 2018. Okay, as you can see in 2011, 99,398 visitors actually came here. Okay, the values that we have in 2012 is different. Take a look at that. And of course, I got a total of the recreation visitors, okay, for the 8 years, okay, that are under investigation. You know what? Because as human being, we are curious, we are very anxious about what is going to happen next. So we want to be able to look at the pattern, okay? We want to look at the trend, okay? We want to see whether there's going to be an appreciable upward movement, or there's going to be an appreciable downward movement, okay? We want to know the trend, okay? When we want to know the trend, so that knowing the trend, we'll be able to predict probably the numbers of visitors that will come in probably in 2019, 2020, and so on like that. Okay, so we need to, four of us, understand the variation in the data set that we have right now. Okay, if you take a look at the data set that I have here, this is time series data because they are collected over time. And you know what, like I said, there's going to be violation of independent assumption. Okay, so if you really want to know, you can actually have a time series plot. What I'm having right now is just a diagrammatical plotting of this, over the years under review. Take a look at that. It started by, going up, there's something that come down in 2014 and pick itself up again. And there's something that starts, to 2017 and it goes down again. Take a look at that. So this is actually the time plot for the data set. Okay, some of you may want to look at the cases of COVID. Okay, like cases of COVID, I got that information last week that there have been increase of COVID again in the US, talking about among the unvaccinated, okay, group of people, okay, they talk about the data variants that mutate so fast. Okay, so if you really want to know, because I don't want to believe in somebody telling me, oh, this, that. I don't believe in indoctrination, but I believe in evidence. So all what I'm just going to do, okay, I'm going to look at, okay, what is it? If I want to look at it if I want to investigate that on a weekly basis, then I'm going to, probably visit the hospital. Then I'm going to know what is it reported, how many cases of the COVID that we have in a particular week. And you know what? If I have data set on so many weeks, then I can actually have a plot to be able to see whether there's going to be a positive trend or there's going to be a negative trend and stuff like that. Okay, now, for the purpose of analysis, what we're going to do, we're going to assign variable for each data. If you take a look at Y1, the Y1, because that is going to be the first data point, right? Then I'm going to call that Y1, okay? The second data point is Y2, and so on like that. So, the notations right here from Y1 to Y8, they are actually the symbolic representation, okay, for the response variable, the time series variable, okay, y1 to y8, then we're trying, so that is how we're going to denote that, okay. Take a look at that. Okay, now a sequence of data that measure the same thing over another period of time is what we call time series, okay. you know um if you take a look at this value here, it represent the same thing as this value, okay, even though we have different values, but they all represent the numbers of recreation visitors, okay, to that particular Mississippi River, okay. And you know what, look at what we wrote there, ordered period of time. This period of times, they are kind of they are ordered, okay. But you know what, in the linear regression that we normally do, I want to tell you, we don't normally order them, okay. They are not that ordered, okay, because the moment they are ordered, and if the ordering has a time, if it is time incorporated, of course that is actually going to become a time series. Okay, now like I said, we're going to use T, which is going to be ordered time index. Okay, so the YT right here, the 1, T equal to 1 means I'm talking about the first year. Okay, T equal to 2 means I'm talking about the second year, and so on like that. Like I said, the unit of time could be year, could be month, could be week, could be day. Okay, and this is what I was trying to talk about the other time, that I said in linear regression, the subscript 1 to n are indices used for ID purpose. They don't necessarily mean the order of the observation. Okay, they don't mean the order of the observation. I'm just trying, to let you see the difference between the time series data set and the data set we use in the linear regression. Okay, so the one in time series, of course, and y1 precede y2 and y2 succeed y1. Take a look at that. These are kind of ordered, and that is what qualify them to be time series data. Okay, now in the topics, in what we want to cover, we got two concepts in time series analysis that we call autocorrelation and stationarity. Okay, we're going to talk about that, and we're also going to talk about the simplest time series model, which we call a white noise model. But let me tell you this, in the regression analysis, the simplest form of the model in regression analysis is intercept model. I think you remember that. But in time series model, the simplest time series model is a white noise. Okay, I'm going to walk you through what we mean by autocorrelation in time series, what we mean by stationarity, and what we mean by the white noise model. Okay, I want to start with the autocorrelation right now. Look at the word autocorrelation. When you have two time series data point. For instance, if I choose a particular time series data point, yt and yt minus 1, yt minus 1 precede yt. Maybe probably I'm looking at 2012 and 2011. Okay. Now, we want to see whether there's a correlation, okay, between observations at different moments. Okay. Now, we're seeking to get a correlation between the current values of the series, okay, and the immediate past. This is the immediate past. Maybe if I'm talking about weekly right now, maybe it is going to be February, and this is going to be like January. And if I'm talking about year, no, I'm talking about year right now, maybe probably I may be talking about 2012 and 2011, 2013 and 2012, and 2014 and 2013 and stuff like that. And that's exactly what we're trying to talk about right here. Okay, now when we make a plot, okay, between the YT and YT minus 1, okay, this is actually what we have. Okay, in such a way, the Y5 is actually one. This. You can see the Y5 right here and the Y6. So I'm just talking about the point that we have. Okay, take a look at that. Okay, now like I said, we can find the correlation between the Y6 and Y7, Y7 and Y8, Y1 and Y2, Y2 and Y3, and so on, like that. Okay, we can actually do that. Okay, so but you know what? In general, the correlation that we have between YT and YT minus one, that is taking into consideration the set of data set that I have, the correlation between the current values of the series and the immediate past is actually 0.65. And of course, this is very high, right? That's a positive correlation, right? Okay. Now, uh, if we look at the correlation between the current value of the series and the immediate past to be this, how can we also look at the correlation between the immediate past and the immediate past? Now, what am I trying to talk about now? Okay. Maybe if I'm actually referring to between 2012 and 2011. I'm just, for instance, but right here, can I have a way to talk about 2012? Probably, to talk about 2013 and 2011. Okay. Can I have a way to talk about that? You can see. So then if you take a look at what I have right here. So if this is 2000 and 12 and 2011, then I can come here to say, okay, you know what, I want to look at the relationship between 2011 and 2010. Look at that. Okay, take a look at that. Okay, so this guy here is different from this guy here. Okay, this is a correlation between the current values of the series and the immediate past. Okay, but here the correlation between the immediate past and the immediate past. That's what I mean. Okay, so can we also get that? Yes, we can also get that, because the lag apart, if you look at the distance between this and this is one. Okay, and the distance between this and this is also one. So they are at lag one. The two of them, they are actually at lag one. Okay, they are one lag apart. It's just like I'm talking about the distance between 2012 and 2011, and the distance probably between 2013 and 2012. So they are, the two of them, they are one lag apart. Okay, that's what we mean by lag one. Now, what if in a situation where I want to look at two lag apart? Look at this. This is two lag apart. Maybe I'm talking about, okay, I want to talk about looking at the relationship between the numbers of visitors in 2014. Okay, if maybe 2014 and 2012. Okay, you're going to see that they are two lag apart. Okay, and of course, that is a correlation between them. Okay, take a look at that. Specifically, what I'm trying to say is just that, okay, if I'm talking about daily data, okay, particularly I'm talking about the Google stock price, right? Okay, so maybe I know the price for today. Okay, then I want to, look at the relationship between the price for today and the price for 2 days ago. Okay, a day before or yesterday. Okay, so that's you're gonna see that that's a two leg apart, because at times they could have relationship, okay, because the price today is Tuesday, right? Today is still Tuesday. Maybe we're looking at the relationship between the price for Tuesday and the price for Sunday, because there's possibility the price for Sunday could actually determine the price for today. You get what I mean? Okay, now when you find the correlation, this is actually what we got. Okay, we have 0.912. Okay, so this is a correlation, and you can see this is a two lag apart. Okay, that is two lag apart. Okay, take a look at that. Okay, now, and that was why I said the estimated autocorrelation at lag two. Okay, the two of them, they are two lag apart. Okay, now that is how that is for the autocorrelation. Okay, we're just trying to say, the autocorrelation is an instrument of independence. Okay, it's an instrument, okay, of independence. Okay, the moment the correlation is kind of zero. Okay, the correlation, if it is very close to zero, then we mean they are independent. But look at what we have. Oh my God, the correlation is so high. So the correlation so high means that this time series are truly independent. Oh, can you guys confirm again? I mean, our time series are truly dependent. That's what I mean. Okay, I'm going to say that again. Because the correlation value is so high. Okay, then we mean that the independence assumption is violated in time series analysis. So which means the series actually depend. Okay, can you guys confirm again? If you guys are still hearing me clearly?
Yep.
Okay, thank you so much. Now we want to go into what we call the weak stationarity. I want to tell you that we have an assumption also in time series. We know time in time study there's a violation of independent assumption, but you know what? Every statistical model actually have assumption that we that we make it to work so great, because don't forget we always going to have stochastic components as part of any statistical model. Okay, you know what? We have what we call stationarity. What do we mean by stationarity? The stationarity means, okay, the mean of time series of variable, they have to be the same over time. Okay, the average, the expectation of a time series variable have to be the same over time. And not only that, the variance have to be constant as well. You remember, I think we borrowed the idea of variance be constant over time from linear regression. One of the assumption of linear regression is homoscedasticity. The homoscedasticity means there should be constant variance, okay, across observation given any predictor. I think you know that. So we are also having that the same assumption area. So, but you know what? Situation where the mean of time series is constant over time, the variance is constant over time. Then we have what we call stationarity. Okay, assumption of time series is that the series should be stationary. Okay, the assumption is that the series should be stationary. Okay, and the only condition under which they can be stationary is that the mean and the variance of the series have to be the same over time. And you know what? If they are the same over time, then what are we trying to say? The other time I talked about like one, right? Looking at the autocorrelation now between any two successive series. Like for instance, the correlation between y1 and y2 must be equal to the correlation between y2 and y3, and so on like that. Since they are like one apart, of course, I'm going to call that rule one. Now, you remember the other time when we're talking about, when we're trying to look at the pattern of the visitors to the zoo, okay, and, the Mississippi, I mean, sorry, to the Mississippi River, rather, okay, we're trying to look at the numbers of visitors that came in, okay, between 2011 to 2018, and I told you the correlation between 2012 and 2011, okay, if you're looking at the correlation between that, that's like one, that's a like one, one they stand apart. Okay, it should be the same. What we're trying to say now, it should be the same as the correlation between 2000 and probably 2014 and 2013. Then 2013 and 12, the correlation between them should be the same. That's what we mean right here for lag one. All the correlation have to be the same. So what we're trying to say, the autocorrelation only depend on the difference of movement. That's exactly what we're trying to say. And the same thing should also be applicable to lag 2. Okay, the same thing should be applicable to lag 2 and also to lag K. Okay, I think I made a mistake right here. This is supposed to be row K. Okay, that's supposed to be row K. Okay, at lag K. Okay, that's what we mean. Okay, so when we talk about stationarity, we mean the mean and the variance have to be constant over time. And of course, for lag 1, we expect the correlation between any successful two time series should be the same across board. Okay, now if you guys understand what I just explained right now, I need you to say to comment yes, or you say yes.
Yes.
Okay, thank you so much. Thank you for confirming that. Okay, now how do we identify non-stationarity from the observed time series? I told you the other time that a very good time series model, okay, should be stationary. That is the assumption. Okay, but it is not all time series that are stationary. Okay, but how are we going to know? Okay, we got it two. Okay, one of the two is to draw a time plot. Okay, and when you draw a time plot, okay, you can actually know whether whether it is stationary or not. Okay, stationary actually means the mean have to be the same over time. But there must not be an appreciable upward movement in the mean, and of course the variance have to be the same over time. But when you take a look at what I'm showing you right now, of course the time series plot shows the variance is not constant. Okay, when you look at the across the values of time point, yeah, you're going to see the variance are not the same. I want you to be looking at this now. You remember what we did in linear regression when we were talking about the residual plot. You remember residual plot? The residual plot, we can actually use residual plots to investigate whether there's for linearity and for constant variance. Okay, now we're talking about the picturing your mind about the variance right now. The variation around here is actually different from the variation around here. Take a look at that. And because of that, our conclusion is that the variance seems to increase as time goes on. Okay, and that is a violation of a time series model, because one of the assumptions in the time series is actually that it should be stationary. And the stationary means the mean have to be the same over time, the variance have to be the same over time. Okay, that's what it means. But right now, what I'm trying to show you right now, there's a kind of violation. And the conclusion here is that the time series is not stationary. And if the time series is not stationary, of course, something needs to be done. Okay, we also have transformation in time series as well, which I'm still going to walk you through as time goes on. Okay, now take a look at this. When you look at the first set of data set, you're going to see what is violated here is the assumptions of the constant variance over a different time period. But take a look at this guy here. The assumptions of constant variance is not violated right here, but what is violated is the mean. As you can see, this is we have an increasing mean. Okay, the time plot indicate that the mean is not constant for all time. Okay, point. Take a look at that. Okay, this actually showed, an appreciable upward movement. Take a look at that. So the mean appears to go up. Look at that. Okay, so here we also have a violation of stationarity here. Okay, so like I told you before, you know, for a time series to be stationary, the mean over time, the mean have to be constant over time, and the variance as well have to be constant over time. I'm sorry, this is supposed to be series. Okay, that's supposed to be series. Okay, thank you so much for Okay, now but sometime I want to tell you, depending on your sample size, using a time plot could be misleading. Okay, using a plot could be misleading. You remember what we did when we are dealing with a linear regression, when I was walking you through, situation where you may not be able to trust your residual plots. Okay, situation where you may not be able to trust your residual plot when you have, a small sample size. You remember I walk you through something like that when you cannot trust residual plot. I also want to tell you in time series analysis, using a time plot could be misleading at times for you to be able to investigate whether a time series is stationary or not. Okay, and that was why I said sometimes the time series plots will mislead us, just like the way the residual plot could mislead us. And I'm going to demonstrate to you an example right now. Okay, it could tell you that a YT is not stationary, and it could be, in actual sense, it could be stationary. Okay, and that was why I said the following time series YT is stationary according to its population model, because when you are specifying a population model and you have already induced stationarity in the population model, and if you now try to plot, to have a time plot, and I want to tell you, your time plot could mislead you by suggesting an increasing mean. Okay, and you now begin to ask yourself what is going on. Like a situation like this, take a look at this. Take a look at what I have right now in simulating this model. Let me first tell you this. When you look in a time series model, we have a YT, okay, um, equal to, we're actually going to have what we call signal, okay, a function of time, and we're going to have noise, okay. Now, just like the way we specify the linear regression model, where we have the explained variation and the unexplained variation. You know what? You know that the explained variation is the deterministic part. Okay, while the unexplained variation is actually the stochastic part. Okay, in time series model as well, we have a signal. Okay, we have what we call a signal, which is more or less the deterministic part. Okay, And of course, we have the random part that we normally want to call a white noise. Okay, and of course, a very good time series model, is a model whose white noise behave well. Okay, if white noise behave well, then of course that's going to be a time series model. So I'm just trying to tell you now, to tell you this is specification of why of a time series model, which is a combination of signal and noise. Okay, but you know what, we have a model right now giving of course this is a noise, okay, that I said, and this is the deterministic part of the model. Okay, what is this is a population model we are suggesting right now, and this is like relating the immediate past with what, with the current. Okay, you are relating immediate past with the current values of this series. Okay, that's what we mean, and in such a way that you are assuming that your white noise, that the noise actually is normally and independently distributed within mean zero. Okay, the expected value of the white noise is zero, and the variance of the white noise is actually 0.19. Okay, that is what you are actually specifying right now. Okay, take a look at that. Okay, now uh, do you know that when we actually, based on this model now, okay, when we have a time plot, we generated, my TA is actually going to walk you through how we can generate data set based on this model. Okay, we can actually generate a data set or some data set based on this particular model that I have here. But you know what? When I generated data set based on this model, and despite the fact that I've already said that this population model here, I've assumed stationarity. I'm assuming stationarity. Okay, take a look at the values that I have. Now, assuming stationarity, okay, if you look at the values for the, what is it called? If you look at the contribution of immediate pass to pass, it's very close to one. Okay, you know, very close to one. It means the largest percentage of what happened today is determined by what? By what happened yesterday, right? Okay, and we are assuming a stationarity. Okay, like thing does not really change over time. Okay, because if the largest percentage, what happened today was actually brought to today, then it means there's more or less a stationarity in the process, right? Okay, this is what the model is actually assuming, and of course the white noise is normally distributed with mean zero and the variance that. But look at the shape. By the time I plotted this time series, look at what we got. Okay, look at what we got. And this is actually giving us the impression that the mean, that this is not stationary because the mean increase over time. Look at that. Okay, and why do we have this? Why do we have a conflict? Okay, I want to tell you the reason why we have a conflict is because of the sample size. The numbers of observation that we used was very, very small. You remember the other time when I was walking you through residual analysis, when I said using a residual plot at time could be misleading. Okay, you remember I walk you through something like that. When we have a very small sample size, there's possibility that your residual analysis could be misleading. Okay, so also in time series analysis, okay, the time plot could be misleading as well. Okay, depending on the volume of the sample size that you are actually using. Okay, and you know what, the time series that we use here actually have 50 observation. Okay, but if you really want to know the behavior, you can actually try more than 50 observation and let us see what happened. Okay, let's collect more data now and let's see what happened. Oh my God, take a look at that. When the number of observation is 100, or can you see something that was increasing before? You get to a point. What happened now? It converged. Look at that. Look at that. Can you see that now? It's showing stationarity right now. Look at that. So when the number of observation is 100, then when I increase that to 1,000, oh my God, take a look at that. The situation is now stationary. Can you guys now confirm now if you're getting what I'm explaining right now? Can you confirm that? Did you guys get that? Did you guys catch that?
Yes, thank you.
Yes.
Okay. Now you can see time series, you can see the time series plot now is behaving like a residual plot that we cannot be that cannot be trusted when the sample size is very, very small. When the sample size is very, very small, you may not really see the you may not have enough evidence to see the pattern. Okay, so when the observation is 50 now, take a look at what we have. I know your conclusion here is going to be, oh, it is not stationary because of the fact that the mean actually increases over time. Okay, despite the fact that the model we are actually using is stationary. Okay, so the reason being that we need to try a good numbers of observation before you can actually see the clear picture of reality. Take a look at what we have right now, and that was why I said once we actually increase the number of observation, then we can now see clearly the time series slowly converges, okay, to 20, and then stay at that value with small fluctuation, okay. And of course, the mean and the variance seem to be constant for t greater than 40. Okay, take a look at what we have right now. Okay, so but I said the increasing trend we see at the beginning, okay, at the beginning is due to an unfortunate starting point. Okay, the starting point, we started from y1 equal to 0. I'm going to show you. We started from, look at that. We started from situation where y1, where the first observation is actually equal to what? 0. Okay, actually you can see that now. Okay, so, and that was why. So, and it takes about 40 time points, okay, for the series to climb out of that valley. Okay, as you can see right here. Okay, look at that. Okay, it takes up to how many? Up to 40 data point. Okay, before you can now start seeing, what we are seeing right now. Okay, that's exactly what I'm trying to say. Okay, so therefore, even though YT is stationary, the first part of the plot misled us to believe that it was stationary. It was not stationary. And that is the reason why at times we need to be very, very careful when we are conducting our statistical analysis. Okay, we got to make sure that, okay, we got to put into consideration that depending on the sample size that we're using, the time plot could mislead. Okay, now coming back to now I want to focus now on the error time in the time series model that I actually call the white noise. Okay, let me tell you this. Why are we talking about white noise? Even in the regression analysis, I told you, because we live in a probability space. The world is probabilistic in nature because the appearance of real world is independent of human knowledge, and there's a lot of variations in this world. And you know what? That makes the world to be stochastic. Okay, and what we normally want to do, we want to have the understanding of the world, right? We want to understand our political environment. We want to understand our economic environment. We want to understand our medical environment, sociological environment, psychological environment, and so on like that. And you know what? For us to be able to understand our environment, of course, what we need to do is actually to collect data. Okay, we need to collect data. And you know what? Collecting data set, the information that we need is in the data set, but it is not readily available. I'm going to say that again. Despite the fact that we know that the information that we need to understand our environment is in the data set, but you know what? The data set that we have, the information are not readily available, and something needs to be done. And what we need to do is to specify a model. Okay, we specify model. Okay, and don't forget the model is a mathematical or statistical representation of reality. And I told you the other time that we're making an attempt to model reality. Model can never be the same as reality. Also, in time series, where data set are collected over time, when we are specifying the time series model, okay, of course, there's always going to be a stochastic component that we call a white noise. Okay, WT is a white noise. And some of you may be wondering, what is the significance of a white noise in a time series model? I want to tell you the significance. It has two significance. Number one, predictability. Okay, predictability. That is number one. Now let me tell you this. If a time series model is a white noise, I told you the other time that the simplest form of a model of a time series model is a white noise model. Okay, like for example, what do I mean by white noise? Maybe I have yt equal to wt. Okay, that's what I mean by white noise model. Now, if a time series model is a white noise, what does that mean? What it means that that is a sequence of a random numbers. So, which means we cannot use that model to make any meaningful prediction. I'm going to say that again. If a time series model is a white noise, and don't forget the simplest form of of a time series model is a white noise model, okay? The one I'm giving you right now, okay? Now, if a time series model is a white noise, then it means that particular model cannot be used to make any meaningful prediction. Okay, that's what we mean. Okay, it means we cannot use that to make prediction. Okay, now another important of a time series model is what we call model diagnostics. Okay, we call that model diagnostics. That's another really another reason why we study a white noise. Right now I'm talking about reason why we needed to have a white noise. Number one, if your time series model is a white noise, then it means prediction will be very difficult to make in that situation. Okay, and number two is model diagnostics. Okay, we the assumption that we place on time series model is that the error time in time series model should behave well. Behaving well is that the error in time series, the forecast error in your model should follow a normal distribution with mean zero. Okay, the expected value of the white noise has to be equal to zero. Okay, now if we have already have a time series model in place and we want to do model evaluation just like what we did in linear regression. In linear regression, one of the assumptions is in linearity, right? Okay, and how do you know whether linearity assumption? No, that is when you look at your residual plots and there's no pattern, then you're going to conclude that the expected value of the error equal to zero, right? But in time series analysis, if you want to evaluate your model, okay, that is, you want to do model diagnostics, the only condition for you to say the white noise behave well or the error type behave well is when it's a white noise. And what does it mean? For it to be a white noise, then it means the expected value of that error must be equal to zero. Okay, we have a way to investigate this. Okay, I just walk you through the reason why we study white noise. Okay, now take a look at this time series model now, where we have the combination of a signal and a white noise. Okay, now that is a signal part, okay, which is the deterministic part of the model. And of course, WT is actually the random part, the one that we call the noise. Okay, this is kind of similar, okay, to linear regression model. Okay, in a linear regression model, particularly in a simple linear regression model, where you have this, okay, you can actually say, oh, maybe the WT is more like E high, right? And of course, the whole of this guy here, maybe probably what I have here. Okay, take a look at that. Okay, that is kind of similar, right? So that is kind of similar. Okay, now let us now assume that the model that we have in right now is a model for daily revenue from an ice cream store. Oh my God! We know we are in the middle of summer right now. We are, of course, I remember yesterday I took my children to an ice cream store to get them ice cream, and I saw that this time around the ice cream store we actually attract a lot of customers because of weather. But you know what, if an ice cream store, if they are interested in modeling their daily revenue, they want to see, is that going to be an appreciable pattern in the daily revenue or not? And they are now assuming a model like this. If you take a look at this model, we're going to call this model auto-regressive model of order one. Okay, we're going to call this autoregressive model of order one, which is AR1. Why do I call it AR1? You're going to see the current revenue. Okay, the current revenue is actually depending on the immediate past revenue. Okay, if you look at the lag distance between the YT and the YT minus one, it's actually one. Okay, so that's what I. So this model now is an autoregressive model of order one. Okay, what I'm just trying to do here, just to break the model into the signal part and the noise. Okay, and of course, what I'm trying to say is that, okay, you know what, the combination of the signal and the noise will give me the observed value. Okay, now I quickly want to, before I go back to the AR of other one, I want to for of us walk you through what I call the white noise model, which is the simplest form of a model in time series analysis. Now take a look at what I have here. The model here is different from the model here. Okay, you can see that the model here contains signal and noise, but you know what, the model here only contain noise. Oh, this is just an intercept. Okay, so this is a noise. Okay, and you know what, this is what we call the simplest form of time series model. And I told you the other time, situation where your model is a noise, then it means you have sequence of random numbers that cannot actually be predicted from one another. Okay, what we mean is just that, okay, that model cannot be used for predictions. Okay, and you know what, the WT is identically and independently distributed with mean zero and variance that, and don't forget C is a constant. Okay, and the two sides stated below were actually, so what we want to do now, I want to generate a time series data set that's a sequence of random numbers. Why are they sequence of random numbers? Okay, because we are actually assuming a noise. Okay, noise model. Okay, and of course we want to use the noise is follows a normal distribution with mean zero. We want to want to simulate data set that have mean zero and variance one. Okay, because that is a noise, right? Okay, like I said, my TA is going to walk you through that. Now in the data set that we generated, okay, this is a plot of that over time. Okay, and we generated two series of data set. When you are generating randomly, of course we can have you know or different kind of data set that will come up. Okay, and we plotted that, and you can see, you can take a look at what we see. Even from the same distribution, you can see different kind of data set that come up, and look at the graphical representation of that. Okay, now you know there's something that we're going to know, what makes it to be a white noise. Okay, we expect the mean it will be within zero. Okay, look at it, this minus 2 to 2, right? We expect them to be within the on average to be within zero. Okay, which I'm going to talk about right now. Okay, using the different kind of lag. Okay, now uh, we're going to talk about a situation. I told you C is a constant, and is that a way from the YT that we have simulated. Okay, uh and which is a white noise. Okay, we want to look at what is going to be the autocorrelation at lag one, what is going to be the autocorrelation at lag two, and what is going to be the autocorrelation at any lag. Okay, and that is exactly what we want to do. Okay, because of that, if you want to investigate the autocorrelation at lag one, it means the YT that we generated from a normal distribution, that is a white noise. We actually want to plot the current values in the series against the immediate past, and this is actually what we are having. You can see, do we have any parent? Does it look we don't have any parent right now. So take a look at part. So because there's no parent, there's nothing like a straight line, and of course it means they are not correlated. Okay, it means they are not correlated. Okay, take a look at that. Okay, when you talk about at lag one, we don't look at that at lag two as well. What are we observing? We're observing the same trend, right? We're observing no correlation, right? Take a look at that. Okay, when you do that at lag three, and when we continue to do that to lag four, to lag five, to lag k, and what you're actually going to see is going to be the same. And you know what? This is actually what we expect. Why are we expecting this? We expect that because the data set that we generated is actually generated from noise, because we expect the noise to have that kind of behavior, because one of the property of the white noise model is that the YT should be independent of others. Okay, the YT should be independent of others. Okay, and you know what? In a time series analysis, we don't. This is not. There's going to be a violation of this assumption. You know that. But what I'm going to say now, what I'm talking about now, is the behavior of noise. We want a situation where the noise, okay, for a noise model, okay, we want a situation whereby there shouldn't be any connection between what happened, in terms of the revenue. Now, for the ice cream shop, okay, the revenue for today should not depend on the revenue for yesterday. Okay, that's what we mean. And it shouldn't depend from the revenue from a day before and so on like that. That's what we mean. Now, YT is independent. Okay, take a look at that. Okay, and in fact, for any two moments, okay, R and S, okay, we expect them to be independent. Oh, can you guys confirm again? If you guys are still hearing me clearly?
Yes.
Okay, thank you so much. Thank you for confirming that. And that's what we mean by the white noise. Okay, now I want to walk you through another example now. Okay, I want to use my sleeping pattern. Okay, Kazeem's your professor now. Okay, your professor or sleeping pattern. Okay, if my sleeping pattern is a white noise, okay, you know what I mean. If my sleeping pattern is a white noise, what that means is that you cannot actually predict the numbers of hours that I'm going to sleep today, and that cannot be determined by the numbers of hours I slept yesterday. That's what it means. When my sleeping hours is a white noise, you get what I mean. So suppose the model for Kazim's daily sleeping hours is this. Okay, the eighth year is just a constant. Okay, so YT equal to WT. So this is an example of a white noise model. Okay, and you know what, the WT actually follow normal distribution, which means zero and variance one. Okay, now if we generate based on this data set, okay, if we generate, the way WT, if you generate WT from standardized normal distribution and you add 8 to that, of course, you're going to have a series of YT. Okay. And if you plot that series of YT against time, okay, this is actually what you're having right now. Okay. Can you see what you're having right now? Okay. Now, what can you actually, based on what you're having right now, you're going to see that the mean is actually going to be 8. Okay. How? Okay, if you want to know, take the expectation of YT, YT equal to WT plus A, right? Expectation we multiply this, going to be that. And don't forget I said the expectation under the assumption of a white noise should be equal to 0. Okay, 0 plus 8. It's actually going to be equal to 8. Okay, that's why you have that. And of course, what's going to be the variance? Okay, don't forget, I'm assuming my WT is as a variance of 1. I think you know that. Okay, now let's take a look at that. What is the variance of this guy here? Okay, if you want to find that, that's going to be the variance of WT plus the variance of 8. Okay, and you know what, the variance of a constant is 0, right? So therefore the variance of YT is going to be the same thing as the variance of WT. And of course, how do I know that the variance of WT equal to 1? Because you have already been told right here that WT has a variance of that. So which means for a white noise model, Kazim's model now has a follow, sleeping daily hours follows a white noise model. Therefore the variance of Kazim's sleeping hours is also going to be the variance of the white noise. Okay, that's exactly what we have now. Okay, you guys confirm again. If you guys are still hearing me clearly.
Yes.
Okay, so that is how we got that. And you know what? The autocorrelation, when you take a look at autocorrelation 1, okay, what does that mean? Okay, it's just telling you the correlation between probably the YT and YT minus 1, the yt minus 1, and yt minus 2, the correlation between any two time series variable that is one lag apart, okay, must be the same as the correlation between the one that are two lag apart and so on like that, and they must all be equal to 0. That is what we mean. They must all be equal to 0. Okay, so all this actually hold for a white noise model. Okay, so all what we're trying to say, the autocorrelation at any lag k should be 0. That's what we mean. Okay, now the question now is this model consistent with common sense? We really want to know. Are we trying to say the numbers of hours Kazeem is going to sleep in one day? Are we trying to say it does not depend on the numbers of hours Kazeem slept in the subsequent in the previous existing days? Is it consistent with common sense? We're going to find out. We're actually going to find out. Okay, now that is going to be the end of the part one uh, of the lecture today. Before I go into part two, is there anyone who actually need clarification? Is there anyone?
I think I'm good.
Okay, give me 1 second before I wanted to give me 1 second. I want to use the bathroom. 1 second before I start part two. Thank you. Okay, can you guys confirm again if you guys are seeing me clearly? Are you guys hearing me clearly?
Yep.
Yep.
Okay, want to welcome you to part two of my lecture today. The part two today, uh, I'm gonna be we're gonna be talking about the autoregressive model of order one. Okay, in part one, I introduced you to time series analysis. And of course, I walk you through the simplest form of a time series model that we call a white noise model. And of course, I actually, walk you through the specification of a time series model that's actually going to involve signal and noise. Okay, and I also walk you through the one that involve only the noise alone. Okay, but you know what? What I want to walk you through in this material is autoregressive model of order one. Okay, we want is a time series model, that relates the current uh values of the time series to the immediate past. Okay, and of course, in the model we're going to have a signal part, we're going to have the noise. Okay, so that is what I want to walk you through. Okay, of course, the last time I talked about the concept of autocorrelation, the stationarity, and the simplest form of a time series model that we call a white noise. And of course, I also walk you through the significance of a white noise, in time series analysis, okay, for predictability and for model diagnostics. Okay, but you know what? I want to start uh, using the example that we did the other time, which is this example. This is an autoregressive model of order one. And why is it an autoregressive model of order one? You can say the current values of the series is actually related to the immediate past. So take a look at that, okay? And that which is similar to the conventional linear regression model. And of course, I remember I was using the example on the daily revenue from an ice cream store. Okay. Okay, now, and I remember I also walk you through in the last material, I walk you through a white noise model where I actually simulated series of data for Kazeem, your professor's sleeping hours. Okay, and of course, I walk you through that, and we realize that the mean of the time series variable actually equal to 8, and the variance equal to 1. The variance of the YT that is that follows a white noise model will have the same as the variance of the white noise. Okay, I think I walk you through this, and I also told you the autocorrelation at any lag will be equal to 0 for the autocorrelation at any lag will be equal to 0. That is for white noise model. That's for white noise. Okay, I just wanted to take note of that. But what is new now? What is new now is what we call AR for that one. That is what we call auto-regressive. Okay, the AR means auto-regressive. Or for that one actually means I'm actually relating the current values of the series to the immediate past. If the unit of time is year, okay, maybe I want to relate this year with what happened last year. If it is month, maybe this month with last month. If it is day, maybe today with what happened yesterday. Okay, that's what I mean. Okay, now I'm going to walk you through an example right now. The model we are specifying now, the general form of autoregressive model of order one is this. Okay, take a look at that. That is the general form. Okay, if we want to talk about population model, okay, autoregressive model for that one is that. Okay, we're going to have the combination of the signal and the white noise. Okay, and of course, we are actually defining our white noise, the random part, so follows a normal distribution, which means 0, and the variance that. Okay, take a look at that. Now, if you compare this guy with this guy, all what we are assuming is that our C naught is actually equal to 0.8, and our C1 is actually 0.9. Okay, some of you may be wondering, what is C naught? That's a constant, right? That is more or less like an intercept. But you know what your C1 here is? The C1, here is going to be representing rho, which is autocorrelation. It's going to be representing rho. And you know what? The rho lies between 0 and 1. Okay, that is autocorrelation. And you know what we're trying to say here, 0.9 is the autocorrelation, between, the correlation between the YT and the YT minus 1. That is exactly what we're trying to talk about. But you know what? Alternatively, if I don't want to specify the model like this, I can specify the model in a main form. Look at that. So another way to specify this is to do it like this. Look at that. So this is also the same thing as this. And you know what? In this model, the mean is 8. Okay, I'm going to show you the reason. Some of you may be wondering, how do we get mu to be equal to 8? Okay, how do we get that? I'm going to work that out now. Okay, I'm going to work that out with you now. Okay, now let's find the expected value of YT. Okay, let's say for this time you want to find the expected value of that. Okay, and the expected value of the other side, right? So expected value of YT, okay, will be equal to, what is the expected value? So expected value of 0.8, okay, plus expected value of 0.9, okay, YT minus 1, plus the expected value of WT, okay, when you take the expectation of both sides, right? Okay, the expected value, also, if you continue that way, expected value of YT, what is the expected value of 0.8? It's also going to be 0.8. Expected value of a constant is a constant, right? Plus, this guy here is going to be equal to 0. Don't forget, we have said that WT has a mean of 0, right? The expected value of WT will be equal to 0. Now I'm left with this. Okay, this is going to be 0.9 expected value of YT minus 1, right? Now, I told you the other time that for stationarity, okay, the mean of different time series should be equal, right? Now, because of that, I'm going to say expected value for stationarity, expected value of YT should be the same thing as expected value of YT minus 1. Now, right here, okay, you know what I'm going to have right now? Okay, I'm actually going to have expected value of YT equal is 0.8, okay, plus is 0.9 expected value of YT. Okay, now solve the equation for expected value of YT. Okay, if you want to solve, if you want to solve the equation for expected value of YT, okay, you're gonna see what you're gonna have right now. Okay, it's gonna be, if this guy should go to the other side, I'm actually gonna have expected value of yt into 1 minus 0.9, okay, which is equal to 0.8. Okay, and if you take a look at this guy, that is be 0.1, right? Divide both sides by 0.1. Okay, when you divide both sides by 0.1, okay, your expected value of yt will be 0.8 divided by 0.1, which is going to be 8. And what is the expected value of yt? That is a mu. Oh, can you guys confirm if you guys catch that? Did you guys catch that? Did you guys understand how the expected value of yt become 8?
I think so.
Okay, okay, so that is how we derive. So, and that very 8 is what you have here. Okay, another specification of the model is to write yt minus mu. And of course, the mu is expected value of yt. Okay, that we derive. I can give you a model like this, and I can ask you to derive the expected value of yt. We can also ask you to derive the variance of yt. Okay, now take a look at that. So this is another way to represent the model. Okay, so this is representing the model in a mean form. Okay, take a look at that. So the two of them they are the same. Okay, now, and what I just show you right now, this is a proof. Okay, if you're given a model, a time series model, an autoregressive model for the one like this. Okay, and you were told that the WT, the white noise, follow normal distribution with me 0 and that. How can you actually find the expected value of yt? Okay, this is what I just did right now. This is what I just show you. Look at that. That's what I just did. Okay, where we're going to say, okay, given this, take the expectation of both sides. Okay, what is the expected value of 0.8? This is 0.8. Then you're going to take the expectation of this guy here and the expectation of this guy here, right? And the expectation of WT is 0. Look at that. Expected value of WT is 0, which is the mean, right? If this is 0, then I'm going to have just this. And you know what? Under stationarity rule, okay, the expected value of yt should be the same thing as the value of yt minus 1. Okay, which means I'm actually going to plug in expected value of yt here. Then I'm just going to solve for expected value of yt, and that is going to give me 8. Is there anyone who is not clear about I derived the expected value of yt to be 8? Is there anyone?
No, I think I'm good.
Are you good, right?
Yes.
Okay, if you guys are good with what I just explained right now, you comment yes or you say yes.
Yes.
Yep.
Okay, thank you so much. So which means I'm confirming to you in exam, I can give you any form of AR of other one or other two model, and I ask you to derive the expected value of yt, which is the mean. So this guy here is the mean that we're talking about. Okay, now how can we now find the variance? We've already found the expected value of yt to be this. Okay, and I'm going to walk you through how to find the variance right now. Now take a look at this. I want to find the variance now. Okay, this is the yt, right? And I want to find the variance of that. But you know what? This guy is a constant, right? The variance of a constant is 0 if a constant does not change, right? So which means the variance of this is just going to be the variance of just this alone. Look at that, right? Take a look at that. Okay. Now you remember in statistics, the variance of x plus y is the same thing as the variance of x, okay, plus the variance of y if we assume x and y are independent. Okay, now we actually want to make use of that's what we're trying to use right here. Take a look at that. We're using the law in statistics. The variance of the sum of random variables we know is going to be equal to the sum of the respective variance of each variable. That's what we have right now. Okay, take a look at that. Okay, now when you have this guy here, you remember that the variance of ax, where a is a constant, is a squared variance of x. Do you remember from statistical principle? The variance of as, where a is a constant, is going to be a squared variance of x. Okay, so take a look at this guy here. 0.9 is a constant, and I'm going to square, and that was how I got it. So I'm using this law. Look at that. Okay, and what is the variance of wt? The variance of WT is 0.19. How do I know? Okay, you have already been given here. I'm gonna look at that. Where WT follows normal with mean 0 and variance that. Okay, this is the variance. of WT. You're just going to plug that in. Okay. Instead of variance of WT, you're plugging in 0.19. Take a look at that. Okay. And this is, and don't also forget, what we have now, this is where we are now. Okay. Where we have the variance of YT is actually equal to zero point 0.9 squared variance of YT minus 1 plus 0.19. Now, you remember the other time, the stationarity rule that said that the variance of YT must be equal to the variance of that. You remember under stationarity, the mean have to be constant over time. The mean of the series have to be the same over time. The variance of the series have to be the same over time. Now, because of that, we are actually going to use the fact that the variance of YT equal to variance of YT minus 1 based on assumption. Wherever we see the variance of YT minus 1, we're going to plug in the variance of YT. Oh my God, what are we going to do now? We're just going to solve equation. We find ourselves back in high school where we needed to solve for equation. What are we solving for? We're solving for the variance of YT. And at the end of the day, this is what we got. Is there anyone who do not understand, who doesn't understand what I just explained right now? Is there anyone?
No, I understand it.
Okay, that is the way, that is the right. I'm confirming to you, you can be given something like that, and they ask you to derive the mean and the variance of that. Okay. Okay. Now, what we just did right now, given an ARO of order one, we've derived the mean of the series, we've derived the variance. Then another important measure that we can talk about is the correlation. Okay. Can we have a way to find the correlation at lag one given the series? Okay, at lag one, okay, which is called row one. And what row one means, we want to find the correlation between YT and the YT minus one. Okay, at lag two, we want to find the correlation between YT and YT minus two. These are two lag apart. Okay, we can continue that way, and we're actually going to look at the pattern. Okay, we're going to look at the pattern. Okay, now let's get started with that. You want to find correlation at lag one, which is the correlation between the YT and the YT minus one. I think I'm actually going to stop here today. I don't want to rush you. I'm going to start from the correlation tomorrow. I'm going to start from here tomorrow before I go to the tomorrow's material. I don't want to rush you, but before tomorrow, you can actually be looking at this the way I did it. It's kind of easy. We have some assumptions. Like I said, that is where I'm actually going to start from tomorrow. I don't want to rush you, but I want to have a question time based on what we have done now. Is there anyone who want to ask question or who need clarification? Is there anyone?
I actually have a question on the homework, on homework 5.
Okay. You have question on homework 5.
Yes, so it's about
Okay.
the Titanic data. So, um, I wrote out the Titanic, the fitted model, and it's survival, plus intercept, plus, there's several classes of passengers, right? There's class 2, 3, as well as 1. Um, and then you have age in the model as well. So one of the questions asks, um, how do you describe age relative, or the slope of age in this fitted model? And because age is not binomial, how would you describe that in the fitted model compared to everything else?
Yeah, you remember the other time when we were dealing with looking at the effects of how does age, when we're talking about something that has to do with people who travel for adventure and who travel for cultural, where we said how does age relate to the amount for those who travel to adventure and who travel for cultural. Of course, you're actually going to use that idea in that logistic regression where so you're also going to use that. Does that make sense to you?
Yeah, so I compared, age to passengers in class one. So like I said, compared to, passengers in class one, the odds of survival, you know, decrease or increase by a percentage based on the formula, the EXP formula, on average for every year older, right?
Yeah,
Is it
you
on
you you
average?
you 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 can actually do that. One of the predictors is actually continuous, and of course, you know, when you want to interpret the slope, what I want you to do, like revisit the lecture slide, where how for in a situation where you have the combination of continuous predictor and categorical predictor, how do we normally interpret the slope associated with the continuous predictor with regard to the categorical predictor? Okay, so if you revisit the
Okay.
lecture slide on that, you're actually going to be fine.
Okay,
Uh,
sounds good.
you understand what I mean, right?
Yes.
Okay. Okay. Okay, I want to thank everyone because, like I said, I don't want to rush you. This is a new topic, and I'm going to start from the autocorrelation tomorrow. Okay, because this is a new topic. Um, of course, I want to take things so slowly because what we're doing now, the time series, we dominate the final exam. Okay, and that is why I actually want to take it so slowly. But you know what? I'm going to release the final practice question tomorrow, Wednesday. Okay, I'm going to release the final practice question. Um, for the final practice question, is going to be cumulative. Okay, it's going to be cumulative. Okay, but a good number of what we did from logistic regression to time series will take about 70% of the final, while the remaining 30% will come from linear regression and the other things that we've done. Okay, I'm going to say that again. Uh, from logistic regression to Poisson regression to time series, they're actually going to play a huge role in the final. 70% of the question in the final will actually come from Poisson regression, logistic regression, and the time series that we're doing now. While the remaining 30% will come from other topics that we've done before now. But you know what? Tomorrow, Wednesday, I'm actually going to publish the the final practice question. And you know what? The midterm too will be graded by myself because a lot of students, the reason why I'm going to grade the midterm to myself is because I receive a lot of, you know, information from my student, get feedback from some student, what they experienced during the exam, and because of that, because I have the knowledge of their complaint, of course, I'm really one that will grade the midterm to myself. Okay, and I also want to use this opportunity to remind you, um, it is the time that students are required to fill up student rating of professors. Okay, you can check that on the course Canva. The university actually need that information from you, and that is good for the system because we need to hear from you. The university want to hear from you the way we have been conducting our lectures, and that is fantastic. The university need that to move forward. Okay, I want to appreciate everyone who have attended my lecture today, and I hope you guys enjoying it. And until tomorrow, then I'm actually going to come your way again. Make sure you stay safe and have a good day, guys. Bye for now, everyone.
Bye. Thank you.
You're welcome.